Let's talk about quantum entanglement. It is, without a doubt, one of the weirdest and most important ideas in all of science. For almost 100 years, it's been messing with our definition of reality itself, and right now, it's literally building the world of tomorrow. To get how we got from there to here, we have to start with the guy who gave it that famous, spooky name.
You know, the whole story really kicks off with its most famous critic, Albert Einstein. He just could not get on board with quantum mechanics, and in 1947, he called it spooky action at a distance. And that one phrase, man, it just perfectly captured this huge conflict that would end up driving physics for the next 80 years.
So to really understand why he was so bothered by it, we've got to rewind to 1935. Einstein, along with a couple of colleagues, Podolsky and Rosen, came up with this brilliant thought experiment. We call it the EPR paradox. And here's the kicker. They didn't design it to prove quantum mechanics. They designed it to prove it was broken, that it had to be missing something. And this right here, this is the heart of the fight. It's two completely different views of how reality works. On one side, you have Einstein's gut feeling, which we call local realism. It's simple, right? A ball is red even if you're not looking at it, and nothing, absolutely nothing, can travel faster than light. But then you've got quantum mechanics over on the other side saying, nope. It predicts that some particles have no definite properties until you look, and that they can be linked so that measuring one can instantly, and I mean faster than light, affect the other, even if it's across the galaxy.
So what is this crazy link? Well, it's quantum entanglement. And here's the crucial idea to wrap your head around. When particles are entangled, they stop being two separate things. They become a single, unified system. You might know everything about the system, like, say, their total spin adds up to 0, but you know absolutely nothing about the individual particles. They're in a total state of limbo until, boom, you measure one. The second you do, the other one, wherever it is, instantly snaps into the opposite state. For decades, this was just a debate, something for physicists to argue about over coffee. Einstein said it was impossible, just a flaw in the theory. The quantum guys said, hey, the math works, but how could you actually solve it? I mean, how do you put reality itself on trial? That question just hung in the air for years, until one physicist had a breakthrough. In 1964, this guy, John Stuart Bell, just changed the entire game. He came up with a mathematical theorem, a real test you could do in a lab. It basically put a speed limit on how connected two particles could be if Einstein's view of the world was right. But quantum mechanics predicted that entangled particles would blow right past that speed limit. And just like that, it wasn't philosophy anymore. It was a real, testable, scientific showdown. And that kicked off this amazing multi-decade race to figure out what reality is actually like. I mean, the first hints of entanglement were seen way back in '49, but the first real test of Bell's theorem didn't happen until 1972. The real heavy hitter was an experiment by Alan Aspect in 1982, and that was followed by a whole series of even better so-called loophole-free tests, with the final nail in the coffin coming in 2015. And the verdict? Oh, it was beyond decisive. Aspect's experiment didn't just disagree with Einstein's view, it absolutely shattered it. His results violated the classical rules by an incredible 242 standard deviations. Look, in science, 5 standard deviations is a discovery. 242 is just game over. It's a certainty. Einstein was wrong. The universe really is spooky. Okay, so once physicists proved this spooky action was 100% real, the next question was pretty obvious, right? Can we use it for something? And the answer to that has been a resounding yes, turning entanglement from a weird paradox into one of the most powerful tools we have. And today, that tool is the foundation of a whole new tech revolution. We're talking about communication that is physically unhackable. Because if anyone tries to eavesdrop, they break the entanglement and you know immediately. It allows for a kind of teleportation, not for people, but for pure information. And it's the key to building super secure global networks that bounce signals off of satellites.
All right, let's unpack that teleportation thing because it's not Star Trek, but it's just as cool. Imagine 2 people, Alice and Bob. They each have one particle from an entangled pair. Now, Alice has a third particle, a qubit, whose state she wants to send to Bob. So what does she do? She does a special measurement on her 2 particles and then just calls Bob up or sends him an email with the result. Just 2 regular bits of information. Bob gets that message, does a little tweak on his particle, and like magic, his particle instantly becomes a perfect clone of Alice's original.
The information, the quantum state, has been teleported.
And this stuff is not just stuck in labs anymore. It is going global, and I mean that literally. We are in the middle of a full-blown quantum space race. China's Jinan-1 satellite already created a link over almost 13,000 kilometers. NASA is putting self-healing quantum bits on the International Space Station. Europe's building its own system. We're building a truly entangled internet in orbit.
And a huge breakthrough in 2025 just flipped the whole strategy on its head. See, we used to think you had to build these super complicated, delicate sources of entangled particles onto the satellites, which is expensive and difficult. But we've just proved you can keep the fancy hardware safe on the ground and just beam the quantum signals up to much simpler satellites. This is a game changer. It makes the whole network way cheaper, way easier, and way more scalable.
So for a really long time, we all kind of assumed this quantum weirdness was just for the little guys, single atoms, single photons. But the next big frontier is proving that this stuff, entanglement, can happen on a scale that you could actually see, that you could hold in your hand.
And guess what? We're already there. The 2025 Nobel Prize went to scientists who built these tiny circuits where trillions of electrons all march in lockstep, acting like one single quantum object. We've now entangled tiny drumheads made of quadrillions of atoms in what people are calling quantum sound. Even at the crazy high energies of the Large Hadron Collider, we've seen it between massive top quarks. Spookiness isn't just for the small scale anymore. It's everywhere. And if it's everywhere, well, that leads us to the most mind-bending question of all. Is it also inside of us? Could quantum entanglement be a part of biology itself? Could it be happening inside our own minds?
The wall between physics and biology is just crumbling. In this amazing discovery from 2025, scientists actually managed to get a living cell to produce a special protein, a protein that acts as a working quantum bit, a qubit, which is the basic building block of a quantum computer. Just let that sink in. We are now doing quantum engineering inside living things.
And this just opens the door to some incredible and pretty controversial ideas. There are theories, like one called ORC-OR, that suggests consciousness itself might be a quantum process happening inside our brain cells. And we're starting to get evidence. It looks like anesthetics might work by shutting down these very quantum effects. And maybe the most shocking thing of all, recent MRI studies have found the first actual physical evidence of large-scale quantum entanglement in a living, working human brain. Now, let's be real. The biggest challenge for any quantum technology is that these states are incredibly delicate. A stray bit of heat or vibration can destroy them. But it looks like we're finally turning a corner. In late 2025, a team at Harvard built a system that crossed a critical line in the sand, something called the error threshold. That's the tipping point where building a bigger quantum computer actually makes it more stable, not less. This is it. This is the light at the end of the tunnel for building quantum machines that can actually solve real problems. So think about where we've been. We started with a spooky paradox that bothered one of the greatest minds in history. Now it's a proven fact of our universe. It's become a tool that's building our future technology, and it might even be a key to understanding life itself. It shows us that reality is so much more deeply and strangely connected than we ever could have imagined. And that leaves us with one last big question. If these invisible, instantaneous connections are woven into the very fabric of everything, what else are we not seeing?